So it is a great pleasure to have with us Professor Serguei Komissarov from the University of Leeds. It's a great pleasure having with us Sergei. He did his PhD and master's at Leningrad State University. He was then a research scientist at Lebedev Physical Institute in Moscow, a postdoc at Manchester University and Leeds, and then lecturer, reader, and full professor at Leeds University. Sergei has a great contribution on astrophysical jets, on various problems involving relativistic hydrodynamics and magnetohydrodynamics, where a lot of us keep his papers on our desks to read. They are very, very useful for all of us. So without much further ado, I would like to welcome Sergei, who is going to talk to us about electrically charged black holes and the Blandford-Znajek mechanism. So Sergei, if you want to share your screen and start your seminar.
Okay, so let's start with the introduction. In this talk, I will be telling to you what I know about electrically charged black holes and the connection of the electric charge to the Blandford-Znajek mechanism. And it will be kind of a storytelling. All the conclusions will be made in the process of this talk. All right, and the structure will be kind of continuously flowing, and I will stop whenever it's necessary. Okay, so let's start with the introduction. And I will discuss, first of all, the electromagnetically driven outflows from rotating conductors. And the most famous example is the Faraday disk. So we've got, well, this disk, it's conducting, it's rotating, it's got the magnetic field, which threads the disk. And the charged particles which are rotating inside the disk are subject to the Lorentz force, V cross B. And this force, direction of the force depends on the charge, and it causes the charge separation. So free charges move, let's say it's electrons move to the outside, to the edge of the disk, and there is a deficit of the charge in the inside of the disk. As a result, we've got the charge separation and the difference of in the value of the electrostatic potential between the center and the edge of the disk. Right, and this is a battery with a potential difference. If we connect the center and the edge of the disk with a wire, then we'll have an electric circuit, and the current can flow, and we can, let's say, introduce some load as a part of the circuit, and we can use the energy of the current in order to, say, light a bulb, for example, or drive an electric motor. Okay, so this is Faraday disk is a proper battery, and it's got its electromotive non-electrostatic force, which is the Lorentz force. All right. Now, in astrophysical applications, we don't have, well, these wires. We've got plasma above and below this disk, right? And the magnetic field lines work as a wire along which, well, this free charges of plasma can flow. And as a result of the current which flows along the magnetic field lines, we've got the azimuthal component of the magnetic field. And as a result of the rotation, we've got an electric field, which is radial, and the dot product of those two fields creates the outgoing Poynting flux. Okay. And as a result of this Poynting flux, well, the rotational energy of the disk can be extracted, and later it can be used, this energy, in order to do some work, let's say accelerate an outflow, or do some dissipation, some heating of plasma further out. Okay, if you have a different kind of rotating conductor, let's say star or a ball, right? And we still have this magnetic field threading this conductor. Then everything proceeds more or less the same fashion. We still have this Lorentz force, which is the electromotive force of the system. It creates the charge separation, potential difference, and so on. So now let's move to the electromagnetically driven outflows from black holes. And in this case, well, there are some similarities with the previous examples. Well, first of all, the black hole is rotating, and there is a rotational energy which can be extracted. And Penrose found the mechanical process a long time ago in 1969, which allows to extract all this rotational energy. And the key region in this process is the ergo region, just between, well, the event horizon and the surface called the ergosphere. So this close region to the black hole plays an extremely important role in the Penrose process. Also, if a black hole is placed, a rotating black hole is placed in a line uniform magnetic field, then there is a electrostatic potential drop along the axis of this rotation. And it was found by Wald in 1974, also quite a long time ago. And this result stimulated Blandford-Znajek to look for steady state axisymmetric force-free plasma outflows from the black hole, and they found a solution. And the plasma in this model is supposed to be created like in the magnetospheres of neutron stars, where gaps, where we've got a copy of spare production. Okay, but there are some differences from the previous examples. In the case of the black hole, we don't have any rotating conductor. So black hole is not a rotating conductor. So all we've got is just a highly deformed space-time. And as there's no conductor, there's no electric charge separation to generate the electric field. And there's no electric battery with electromotive Lorentz force. So this is clearly very different from all the previous examples. And as a result, there was quite a poor understanding of the Blandford-Znajek mechanisms, how exactly the rotational energy is extracted in this mechanism. For example, Blandford-Znajek will make the following statement in their paper. This process is somewhat similar to that of Penrose if you think of it in terms of particles inside the event horizon, interacting with particles a long way from the hole through the agency of magnetic field. Well, we know, of course, the null signal originated inside the event horizon can propagate outside, and so this is a very bizarre statement. Later, Forn, Price and McDonald introduced the so-called membrane paradigm, where the event horizon is attributed to the whole range of physical properties, but this is a complete artificial construction. Okay, there is no membrane. And Punsley and Karaniti, as a result of these issues, they declared the Blandford-Znajek solution unphysical on this causality argument. So because the horizon, event horizon, and the interior of the event horizon are causally disconnected from the outflow, they cannot influence the outflow, they cannot create the outflow. And well, this poor understanding continues until I thought I explained it all in my 2004 paper on the magnetospheres of black holes. But recently, King and Pringle in 2029, in fact, well, they published a paper. They put forward quite an interesting argument. And well, first of all, they looked carefully at the paper by Wald. And Wald argues that the black holes, initially uncharged black holes, in his configuration, where the black hole is placed in a uniform aligned with the rotational axis magnetic field, they should attract an electric charge of one particular side, and they will keep attracting it until this will nullify the electrostatic potential drop between the horizon and infinity. And well, this charge is related to the spin parameter of the black hole and the strength of the magnetic field at infinity. And he argued that the Hel potential, okay, right, and right. So if there is no potential drop, then there is no essentially electric field which can drive the current. Right, and then Pringle noticed that for this value of this charge of this Wald charge of the black hole, the Hel potential looks exactly the same for non-rotating black hole without charge. But non-rotating black holes cannot drive Blandford-Znajek outflow, and therefore, when the black hole accumulates this Wald charge, the Blandford-Znajek mechanism can no longer operate; it gets nullified. And I decided. Those arguments look quite simple and quite convincing, and I decided to look more carefully at the work by Wald and see what's going on. Okay, let's start with a quick look at the Wald solution. All right, and it's based on the following fact that an axisymmetric steady-state vacuum solutions for the full potential for an axisymmetric steady-state vacuum solution can be written in terms of Killing vectors. Right. So here M is azimuthal Killing vector and K is a time Killing vector. So those are vectors related to the two symmetries of a rotating black hole: symmetry with respect to time and symmetry with respect to azimuthal angle. Right. Okay, so if we introduce this potential, then it will satisfy the equations of electrodynamics. And then Wald started looking for astrophysically interesting solutions, and he's found the following solution. All right, and the solution has two properties. Well, first, there is zero electric charge on the black hole, and then at infinity, the magnetic field is uniform, has strength B naught, and it is aligned with the black hole symmetry axis. Okay, and what were Wald's arguments for charging of black holes? So he used the potential, which I discussed before, and he evaluated the change in the electrostatic energy of the particle with the charge QP between the horizon and infinity along the symmetry axis. Okay, and he found that it's non-vanishing, and it's related to the strength of the magnetic field and the rotation parameter of the black hole in the following way. And because it's not vanishing, the charges of one sign are accreted by the black hole if these charges are somehow created outside of it, and the charges of the other sign are repelled. And the black hole gets charged with it. Okay. And if there is a charge on the black hole, then the potential becomes slightly different, the Hel potential. Well, a new term appears, which is related to the charge of the black hole. And as you can see, it has exactly the same form as the second term here in the brackets. So it's the same Killing vector which is involved. And for some value of the charge, those two terms will cancel each other. And as they cancel each other, essentially the rotation, the spin parameter disappears. And you may guess, because from the fact that the spin parameter is present here in this equation, that now the difference in the electrostatic energy of the particle will go to zero in this case. So as charge gets closer to this particular value, which is called the Wald's charge of the black hole, well, those two terms cancel each other. This is how now the potential looks like. and the potential difference along the axis is 0. And Q naught is called the volts electric charges of black holes. Right? So as the potential difference is 0, then no more charges are accumulated. So charge concluded that the electric field will acquire this charge, and then no more charges will be accreted. And as we pointed out, that he calculated, well, this energy, injection energy, how he called it, only on the symmetry axis. And he just argued that it will be the same for any other point in the horizon. So essentially, he treated the horizon as an equipotential surface. Okay, and now let's look again at the King and Pringle's argument against the Blandford-Znajek mechanism. So first, essentially, they just stated the results by volt. So if there is no potential difference, then no currents can be driven. And then they have taken a look at the expression for the potential, for the four potential. In two cases, well, one case where there is a non-rotating black hole with electric charge 0, and then when there is a rotating black hole, but the electric charge is the Waltz electric charge. And in both cases, the potential is given by exactly the same expression. And as the Blandford-Znajek mechanism does not operate for non-rotating black hole, the potential is the same as the potential for non-rotating black hole, then the Blandford-Znajek mechanism should not operate as well. Okay, so at first sight, well, those are very convincing arguments. Okay, so in order to proceed, I would find useful to introduce a 3+1 split, or a 3+1 formulation of black hole electrodynamics. Okay, and so we start with a 3+1 splitting of space-time. So this is the metric. In general, a metric can be written in this form, all right, where, and it's called the foliation of space-time. And so it's split it into space and time. Space has those coordinates x, and time with this coordinate t. So gamma is a metric tensor of this space, and alpha is called the Hel.A.S function, yes, and beta is a shift vector. Okay, so this can be done for any metric. And we can also introduce observers, kind of fiducial observers, which are at rest in space, and the 4 vector is given by this expression. So those are the covariant components of the 4 velocity of the fiducial observers, and it's got only one component, which depends on the Hel.A.S function. Okay, so let's move on, and we can do the 3+1 splitting, corresponding splitting of electrodynamics. So we can write it not in terms of the tensors of space-time, but in terms of the scalars and vectors of space. Right? Faraday tensor, for example, can be split into electric field E and magnetic field B. Maxwell tensor can be split into two other fields, which can also be called, well, electric field, but now D and the magnetic field H. And the electric current can be split into electric charge and electric current of space free vector. So, so here is the tensor of space-time, and here are the vectors of space. J is also a vector of space, and rho is a scalar of space. Okay, so now if we ask ourselves what is the physical meaning of those vectors, then we can come back to this foliation fiducial observers, which are at rest relative to space, and they can do experiments, measurements, and they will find that B will be the magnetic field according to the measurements, and the electric field will be D, given by this vector D, and rho and J are the local electric charge density and current as measured by these observers. All right, so using this newly introduced spatial vectors and scalars, you can write Maxwell equations in a very much familiar form. In fact, it's exactly the same as the Maxwell equations in matter. And the relation between those four vectors is given by those two constitutive equations. And you can see that this relation depends on the parameters of the metric, on the L.A.S function and the shift vector. And so just by looking at this equation, you can make the following conclusion, that vacuum in electromagnetically active, vacuum in curved space-time looks like electromagnetically active medium, because of those constitutive equations. Okay. Right. Let's move on and discuss the four potential. The four vector of potential can be split like usual into the electrostatic potential and the vector potential. And well, the vectors E and B, in terms of those vectors of the scalar and this vector potentials, they can be written in this very well known form, what's known from the classical electrodynamics. Right? It is exactly the same as in Minkowski space. Right. It's important that the phi component, based on this equation, the phi component of the scalar potential is invariant along the magnetic field lines in the case of axisymmetric solution. Right? And we will use this fact in order to plot the magnetic field lines. There will be just the contours of the phi component of the vector potential. Now, if you look at the relativistic Lagrangian for a particle with rest mass MP and the charge QP, then it's given by this expression. So that's the for velocity of the particle, and U is for potential, and yeah, well, this little u is again for the velocity of the particle. And if you write Lagrangian equations using this Lagrangian, then you'll find that there is an energy, redshifted energy, which is an integral of motion of this equation, and is given by this equation. So it also looks very much familiar. It's like the total energy of the particle, which is a combination of the kinetic energy and the electrostatic energy of the particle. So in this regard, the electrostatic potential plays exactly the same role as in the classical electrodynamics. Okay, so now we can have a closer look at the world solution. All right, and I'll start with the answer to the paradox, essentially the paradox by Kim and Pringle. Right, so once again, let me remind you, so they're saying that if we have a non-rotating black hole with no charge and a rotating black hole with ball charge, then the potential for potential is given by exactly the same equation. M is azimuthal Killing vector, an axisymmetric spacetime. And the contravariant components of this vector is just given by the delta function. Okay, so they're the same. For Schwarzschild black hole, non-rotating black hole, and for Kerr black hole, which is rotating black hole. Okay, right. But for us, what's important are the covariant components of the four potential, and they're given by the covariant components of the Killing vector. And if you calculating the covariant components from the contravariant, you use the metric tensor. And you end up with the covariant components are given by the components of the metric tensor. And therefore they depend on the metric. For the Boyer-Lindquist coordinates, those are the components. And you can see that they involved the spin parameter of the black hole. Right, and almost every term, the spin parameter is present. And therefore, even if this expression is the same, then the covariant components of the electrostatic potential given by these equations are different for rotating and non-rotating black hole. Therefore, you cannot conclude that for rotating black hole, the potential will be the same. The electrostatic potential will be the same as for a rotating one. So in fact, the electrostatic potential will be different, and the vector potential will be different. Okay, so now let's look at the world solution. I will present a few plots for different values of parameters of the world solution, or essentially different spin parameters of the black hole and different charge on the black hole. And lines will be the magnetic field lines. Well, those are like this corresponds to the event horizon of the black hole. And color will be used to show the electrostatic potential. Okay, and at infinity, I will set the potential always to 0. And when the potential is 0, the color in the mapping, in the color mapping here will be white. When it's negative, it will be blue, and when it's positive, it will be red. Okay, so now let's look at the solution, world solution for non-rotating black hole without charge. You can see that the magnetic field lines are straight, and the color is everywhere white, so the potential is everywhere exactly the same as at infinity. So obviously, this is a dead case. Right? There's no potential difference, nothing interesting can happen. So this is the world solution for a rotating black hole with no charge. And to make the plots more impressive, I'm using the maximally rotating black hole, so the spin parameter is 1. What you can see, well, that the darker color becomes the larger the negative. The larger the negative electrostatic potential becomes, and so there is a gradient of electrostatic potential along the magnetic field lines pointing outwards, and therefore the electric force, the electrostatic force, will be pulling electric charges towards the black hole. So just like Wald argued. Okay, so, and this is more or less the same along all magnetic field lines which go close to event horizon. And yeah, you may argue that if some charges are introduced into the space around the black holes, and positive charges will be pulled towards the black hole, and the negative charges will be pushed away from the black hole, and the black hole will eventually acquire some charge. Okay, so now let's look at the world solution with the ball charge, with this critical charge Q0, as we discussed earlier, and compare the solution which to the solution with no charge. And in both cases, I'm using all this maximally rotating black hole again. So this is what we got on the left. We already seen this solution, and now we are looking at the solution for on the right, which is for a charged black hole with the ball charge. And you can see that the solution looks quite different. All right, well, different orientation, different geometry of the magnetic field lines, and different values of the potential. As you can see that now it's a red color. Here it was blue, so the potential was negative, and now it's red or magenta. All right, and therefore the potential is positive here. Now, if you look at the axis of rotation, you will see that the color is everywhere white, and it means the potential here is 0, right? The same as at infinity. So this is exactly as a volt calculated along the symmetry axis, but it's not the same everywhere else. So he argued that it must be the same everywhere else, that everywhere else the potential will be 0, but it's not. Essentially, he made a mistake. He used results by somebody else. And so essentially, he used the fact that the event horizon can be treated as a potential surface. Yes, but this was not, this was concluded for the case where there was no external magnetic field line, a magnetic field. Yes. It was just a black hole and some charge placed in the black hole. And in this case, the event horizon is a deep equipotential. So if you have a magnetic field penetrating the event horizon, this is no longer the case. Right. Also, the potential drop along the field lines which go to the black hole now different, as you can see. So now the positive charges, instead of being pulled onto the black hole, will be pushed away by this potential. Yeah, so the potential increases towards the black hole. Okay, and the negative charges will be pulled towards the black hole. So as a result, the black hole cannot have this whole charge as an equilibrium charge. And if an equilibrium charge exists, then it must be between 0 and the whole charge. And this is indeed was confirmed in recent peak simulations by Prof et al. And they found that there is something like an equilibrium charge, not exactly equilibrium, but more or less it's kind of quasi-equilibrium charge. And it's about 1/4 of the Waltz charge. Okay, now I want you to look again in those two solutions and look at the behavior of the magnetic field lines. So I'll focus on the field lines. Okay, as you can see here, magnetic field lines trying to escape the event horizon. And in fact, it was noticed quite some time ago by a number of authors, in particular by Andrew King and his collaborators. And they noted that as the spin parameter gets closer to unity, so the black hole gets closer to the maximum rotating black hole, the magnetic flux through the event horizon goes to 0. So it becomes completely expelled from the black hole. And this is important because the Blandford-Znajek luminosity, it's proportional to this flux squared. So when the flux escapes from the horizon, we can expect that the luminosity gets to 0. Okay, but now if you look at the charged black holes, you can see that the magnetic field lines are pulled back towards the horizon. Okay, and well, this expulsion of the magnetic field lines from the black hole is called the Mason effect of black holes. Well, by analogy with something similar in superconductors, right? But well, this effect, as you can see from this result, is valid only for uncharged black holes. And if the black hole is charged, then magnetic field lines are pulled back. Okay, so this is an interesting explanation. Well, in fact, in many simulations, MHD simulations, phase-free simulations of black holes, well, the fact that it was observed the magnetic field lines are not pushed away, not expelled from the event horizon, but always show configurations all like this. All right, and at some point, as I argued that this is because of the Hooke stress of the associated with the azimuthal component of the magnetic field lines. But maybe it's not. Maybe it was the wrong explanation, and maybe it's just the charge of the black hole which matters here. Okay, so it's only 5 minutes left. So presumably I should stop here, right? Because I will not be able to finish well this remaining part. And this remaining part, I essentially wanted to explain the nature of the battery of the black hole. And roughly speaking, it's an electric field which is gravitationally induced. So whenever the magnetic field is present, the electric field is also present, and it's induced essentially by rotation, due to the rotation of the black hole. And normally, one would think that whenever we have an electric field, just for example, electric field due to some charged object, if we produce plasma, then the plasma will immediately screen well this electric field because there are lots of free charges in plasma. And you may ask the same question. So what if we introduce plasma? Will it screen the electric field, gravitationally induced electric field in the black hole? And it turns out that it's not. And the ergosphere, the ergo region of the black hole, plays a particularly important region because you can never screen the electric field due to by the free charges of plasma inside the ergospheric region. And in fact, as a result, well, the Blandford-Znajek process is in fact the general relativistic process, and it's an effect which appears only in the case of the strong gravitational field. So the key area is between the event horizon and the ergosphere. Right, so this is all, and I think at this point I will stop sharing.
So thank you very much, Sergei, again.